We remembered in chapter 8 a little bit about what we used to know about sequences. A sequence could be finite or it could go on forever, and we would call it an infinite sequence. A series is a sum of the terms in a sequence. And we could have a finite series or we could have an infinite series. There's a pretty exciting chunk of calculus we can do on infinite series, and that's what chapter 9 is all about. So an infinite series is just an expression that looks like this: the first term plus the second term plus the third term plus the fourth term plus dot 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 plus the nth term plus dot 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 all the way up to the infinitieth term. So you'll use this notation that you've seen before for summing up a bunch of things. So that's sigma notation. That's the big Greek letter E. The numbers, A1, A2, A3, A4, those are the terms in the sequence, which become the terms in the series. And A sub n stands for the nth term. So A sub 2 is the second term, A sub 5 is the fifth term, etc. So if a series means adding together the numbers in a sequence, we could talk about what happens as we add more and more numbers in this sequence, more numbers in the series. What we do, we call that the partial sum. I'm using capital S for sum here. That's pretty conventional notation. So here I have S1, so the first partial sum is just the first term. It's not very exciting. The second partial sum is the sum of two terms, the first term plus the second term. The third partial sum, I would call it capital S with a little sub 3, is the sum of the first three terms, A1 plus A2 plus A3. And then S sub n is the sum of the whole series, all infinitely many terms in the sequence, in the series. And we can use this notation. That's the sum. I'm looking again at the sigma notation. The sum, sk goes from 1 all the way up to infinity of every term in that sequence. Okay, most of chapter 9, the cool stuff that we want to do with series, we won't be able to do it if we can't show that the series converges. So a lot of this early part of chapter 9 is going to be deciding when does a series converge, when does a series diverge. So we had some experience in chapter 8 with when does an integral converge, when does an integral diverge. And some of the math we'll find is the same and some is different and new. So here, very specifically, is the definition of what it means for a series to converge. If the sequence of partial sums has a limit, then the series converges. So limit meaning there's one number that the sums, the sequence of all the partial sums is getting closer to, and that number can't be positive or negative infinity. So for example, we're going to check out this first example. Does the series 1 comma negative 1, well, I should say it like a series, 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus 1, does that converge? Here's your technique, at least at the beginning when we're first understanding what it means for a series to converge or diverge. We need to think about S1 and S2 and S3 and S4, so the first, second, third, fourth, fifth partial sum, and try to figure out, is there one number that those sums are approaching? So the good news is we'll learn some shortcuts for this. But for now, we have to understand what this means and practice it out. So S1 is just going to be the first term, which we've been told is 1. S2 is the sum of the first term, so that's a positive 1 plus a negative 1, which makes 0. The third partial sum is the sum of the first three terms, so that's 1 minus 1 plus 1 makes 1. S4 would be the sum of the first four numbers, which is 0. And you get an idea what's going to happen to these partial sums. They're going to alternate back and forth between 1 and 0. So if I asked you to tell me what the infinitieth partial sum is going to be, I don't know, maybe you could tell if you knew if infinity was even or odd, but there's not one single number that this list is approaching. So this series diverges because the sequence of partial sums does not have a limit. Okay, so check out letter B. Completely different B's letter B. I have a nice slide for letter B. Hold on. Okay, I crossed out that formula because maybe you don't know it yet. But I want to know if this series converges 3/10 plus 3/100 plus 3/1000 plus 3/10,000 plus ... So I'm going to find the partial sum. The first partial sum is 0.3. And the second partial sum is 0.3 plus 0.03, which is 0.33. And the next partial sum, the third partial sum, is 0.333. And the fourth partial sum is 0.3333. So can I tell, is there one single number that this series, this list of partial sums actually, is there one single number that this list of partial sums is approaching? It is approaching 0.3 repeating, which you and I know from experience, I don't know, Algebra 2, that this is the same as 1/3. So yes, there's one single number that my sequence of partial sums approaches, and that's 1/3. So this series converges. We're going to talk a lot more about this series coming up in a minute. All right, so one tool that you definitely need in your tool belt as you embark on this work of deciding whether a series converges or diverges is this one right here. Any series that does converge, you can guarantee that the terms in the series get closer and closer and closer to a 0 as the term number increases. So if you know an infinite series that converges, then it must be the truth that, the limit as the term number goes toward infinity of the term must be 0. So if you ever find a series whose the limit of its nth term is not 0, then you can be 100% certain that that series diverges. Okay, so one of the most important, most important kinds of series that we're going to talk about is a geometric series. So you probably learned all about arithmetic series in Algebra 2. And as good, all that stuff is true, but doesn't really help us too much in calculus. Because to do the calculus that we're about to learn, we need our series to converge. And that means I should be able to find an answer if I try to add up all the terms in this series. If I have an arithmetic series with any arithmetic series that's not consisting of all zeros, then as the term number increases, the sum of my series is going to approach either positive infinity or negative infinity, which is not really super for doing calculus on. So we will I'm pretty sure, I'm going to say this, we're going to talk nothing about arithmetic series in Calculus BC. We're going to talk a lot, though, about geometric series because we have some algebra that we've already learned that can help us a lot with our work here. Okay, so just remember the definition. A geometric series is a series, let's do this. A geometric sequence is a sequence in which the next term always comes from multiplying the term before by the same amount. And we have this convention where we call that amount that we multiply by each time R for ratio. And you can always find R by finding the ratio of one term to the term in front of it. So divide like the second term by the first term, that will give you R. Okay, and then a series is just a sum of a sequence. So a geometric series is just a summing of all of the terms in a geometric sequence. So you probably remember from Algebra 2 or somewhere back there that if R, the number you always multiply by, is between -1 and +1, not inclusive, then the series will converge. And that's probably the first time you ever used the word converge. And all that really meant back then in Algebra 2 is like, okay, you could get a one number answer and it wasn't infinity or negative infinity. So we're going to use that rule. It's supposed to be extraordinarily useful for the calculus we're about to do. So if the number you multiply by every time, which we're going to call R, the common ratio, is between -1 and +1, but not -1 and +1 themselves, then we can find the sum of an infinite number of terms in a sequence added together, of an infinite series. And you might recall, this is going to be key to your success. So if you didn't remember this, you want to write it down, tattoo it on your notebook. If A is the first term in the series, then the sum of that infinite series will be A divided by 1 minus R. Notice that will only work if the absolute value of R is less than 1. If the absolute value of R is greater than or equal to 1, this series will not converge, it will diverge, and you will not get a sum. But this formula, critically important. Remember that you used to know it, and start remembering it now.